Welcome back, ladies and gentlemen. We're looking at sound waves now, trying to apply some of the stuff we've learned about waves in general to sound. To start out, I want to ask, what kind of wave is a sound wave? Would a sound wave be a transverse wave or a longitudinal wave? So let's check this out. Let's say you have a rope and you oscillate the end of the rope up and down. So you create this wave like that, traveling down the rope. And there's the direction of the wave's motion. And what you did to get that wave going down the length of the rope is you had to wiggle it, you had to displace it up and down. In other words, perpendicular to that direction. So if you look at a particle of that rope, you can see that the particle itself is going to oscillate a little bit up and then down and end up back at its original position. Cool. So we've got this transverse wave. Well, let's look at a longitudinal wave and let's see. Classic longitudinal wave is your slinky type of thing, right? Where it's kind of just doing one of these, going back and forth. And that would look a little like this. We got close together, you've got stretched out, close together, stretched out, close together, stretched out. That's a terrible diagram. I'm so sorry. That one's awful. But check this out. Okay, so you see they're compressed close together here, and they're stretched out here. So a particle of the slinky, a piece of it, is going to oscillate that way and end up back where it started. So that would be a longitudinal wave, where the oscillation is parallel to the direction of the wave's motion. Transverse wave, where the disturbance or oscillation is perpendicular to the wave's motion. Arrow for the wave traveling down that way. So what I need you to think about is the air that the sound travels through. So got a bunch of molecules, air molecules, right? Sort of random, going through that molecular motion. Would that be Brownian motion, perhaps? And so what about all those air molecules, right? So the molecules can and do bump into each other. There, of course, are collisions. So this guy might bump into that guy, boom, and they bounce off each other and go on about their way. And it's happening all the time. They can and do bump into each other, but they cannot pull on each other. Right? The molecules don't have any way to sort of attach to each other, and they're not coupled together. That's a good way of looking at this. So, because they're not coupled together, it's only longitudinal waves that can pass through something like a liquid or solid. So, with any kind of fluid, a fluid is any liquid or solid, right? And I guess plasmas also fall into this category with fluids. Only longitudinal waves allowed. Waves I can spell. A transverse wave would not propagate through a fluid. Think about this for a moment, or at least through, I should say, most fluids, I guess. If I took some air molecules over on this side and I shook them up and down, would this air molecule right here moving up and down cause this one to start wiggling up and down? Well, the answer is no, it would not. And there's no connection there. They're not coupled together, not connected. This one might bump into that guy and might bump into that guy, sure, but that would be an oscillation in this direction, and that bump would be a wave traveling in this direction. If I'm trying to get a wave traveling that direction, I cannot do it by wiggling these in this direction. It won't happen. Only longitudinal waves in fluids, for the most part. So here's what this means. Because of this, and we know that sound travels through fluids, the air being a fluid, then sound must be a longitudinal wave. Awesome. And longitudinal waves are sometimes called compression waves. You have right here a compression of the coils in this spring, and here a rarefaction, or they're spread apart more. Compression, rarefaction, and so on. And the compressions correspond to a crest in a transverse wave. The rarefactions correspond to a trough in the transverse wave. So there's still wave properties. There's still an amplitude going on here. And the wave travels somewhere, but the particle in the medium does not. The particle in the medium doesn't go anywhere. It just wiggles and ends up back where it started. Cool. So let's look at this in a little bit more detail. Check this guy out. So I have a tube here, and there's some air molecules in the tube, and I have this plunger in the end of the tube, just a flat surface, and I can move that surface into that air. I can bump the air with this plunger. And what we're going to see happening is as soon as I move it that way, the air molecules right next to it get compressed. All right, fair enough. And these air molecules are not compressed. But what will happen now, because of that compression, these molecules are going to bump into those much more often, and they'll start to push on those more. So it starts to look like this. And now this compression location moves over this way. And at that same time, I'm pulling that plunger back this way. So the bunched up molecules here and the extra space created there on the left ends up creating this rarefaction area where there are fewer air molecules than there normally were. So I have a compression and I have a rarefaction. And then if I'm going to do this compression again, move it into the air, I'll create another compression. So I see compression, rarefaction, compression. And that, if I keep repeating that action of the plunger, it will continue to create those waves. And it's kind of like pressure waves, where you have the air molecules bunched up and closer together. There's a greater density, and lower density, higher density. So you could think of the pressure, the air pressure, as one way to describe this. But watch what's going on. If I look at any one of these molecules, if that were possible, then I see that molecule ends up wiggling back and forth this way. As it does so, it bumps into others, but it just wiggles it back, and as that compression passes by, it just ends up back where it started. That molecule is now buried right in here, and that same molecule is probably right about there, even though I don't have a dot. I'm going to cheat and add a dot right now. Okay, there's that molecule right there. I'm doing that for consistency's sake in my diagram. So it's just wiggling, and the air itself is not traveling down the length of the tube. There isn't a flow of air. There's no wind. It's just the energy. We compressed and added energy. We did work on it. The energy is traveling down. So one more thing here. Check this out. We have a compression and a second compression from one compression to the next. There's a distance right there, or a length you might say. So that is a wavelength, the length of one wave of sound in this air. Cool, huh? Now, that's all well and good. But so what? Okay, well, what about the speed of this wave? Okay, we clearly have a wave traveling down there with some velocity, some speed. Absolutely. And you would imagine, well, it's probably related to some things, like maybe it's related to what it's moving through, like some properties of the air. You might also think it's related to the wavelength. You might also think wavelength is kind of is a distance, and that's the speed, so we need a time, so a period might be involved. If there's a period, you can invert that and talk about a frequency. Well, they are related, so check this out. Here we go. Okay. You recall a relationship like this. This is going to be super important for us. This relationship for all waves, speed of the wave is equal to the wavelength multiplied by the frequency of that wave. All right, fair enough. With sound, okay, sound does have a speed. There is a wavelength. We've actually identified that here, right? And frequency. When we think of the frequencies of sounds. Sometimes we use the word pitch, the pitch of the sound. And you can say higher pitch or lower pitch, and that's what we're talking about. Cool. But let's look at this. Okay, so we're going to apply this to all waves at first. The speed of a wave, so wave speed. For all waves, it's determined by the properties of the medium through which the wave travels. And that's it. So if we look at air that has a greater density or lower density, that will affect the speed. That will affect this guy right here. If we look at a wave traveling through water, which is much more dense than air, then that will definitely affect the speed of that wave traveling through the water. Waves can also travel through solid material as well. So, you know, and many solids being more dense than water even, the speed would be affected and be different there too. Okay. The speed of the wave is related here. We see a relationship to wavelength and to frequency. Absolutely. But in this case, we cannot say that the speed depends on wavelength or depends on frequency. It's kind of the other way around. We know, and it's relatively easy to demonstrate, that the speed of sound in air is right around 343 meters per second. And this is air, maybe you want to get specific, at around 20 degrees Celsius because that gives it a certain density. Okay. And this is roughly equivalent to 770 miles per hour. This is fast. That's fast. But the speed does not depend on the wavelength or frequency of the sound. You can create a different pitch of sound, a different frequency of sound, and it's going to reach someone's ear in the same amount of time as a different pitch will. Otherwise, listening to music would be a nightmare. We couldn't make any sense of it. They all reach our ears at the same time. They all travel at the same speed. So instead, something else must be going on. Maybe the frequency depends on the speed and on the wavelength. And the speed depends on properties of the material. That's the connection you want to know. Properties of the medium the wave passes through. That is what the speed of the wave depends on. Okay. So, you can also say that therefore the speed of the wave is also sort of independent of the amplitude, right? So here, looking at this, the amplitude of this wave. Well, if I compress more and then expand more and then compress more with a greater amplitude of oscillation, that is not going to affect the speed of this wave. It will affect how compressed the air molecules get and how rarefied the air molecules get, but it will not affect that speed. So they're kind of independent of each other. Now, the same holds true for sound waves. Sounds of different frequencies or amplitudes all have the same speed within the same medium, and that speed of sound in air is right there. Cool. Well, that's it for now. This one truly is a short one. I have another important topic coming your way soon. It's still related to sound waves. It's called the Doppler effect, and it's a neat one. Thanks for watching. I'll catch you next time.